Hi, everyone. We're going to go ahead and get started. I'm Prithvi. I am currently a software engineer at Microsoft. I've been there for about 3 years now. I joined right after graduating from Carnegie Mellon undergrad. I'm super thrilled to be here. It's been so much fun. This is my first time at C++ on C. It is my second, of course. It is my second C++ conference. I also went to CPPCon last year in September, also spoke there. Super excited to be here. Also super excited to be here with my co-presenter.
Hello, I'm Kathleen Baker. I also work at Microsoft on the Edge browser. This is my first time at C++ on C, my second time presenting, so I'm very excited to be here.
Okay, before we get into it, I just want to make a quick note that we do have slide numbers in the top right. So if you have a question, we'll take it at the end. But if you could just jot down the slide numbers so we know where to refer back to, that would be great.
But we also have candy on both exits, so feel free to take candy when you leave.
On your way out, yeah. Okay, let's get into it. So we're talking about cutting down on unnecessary extra objects in C++. So as engineers, you all know we do a lot of iterating on feedback. We do a lot of giving feedback. And so over the years, we've noticed certain patterns where these extra objects are created. And so we want to spend the next hour talking about what these patterns are, and then going over some strategies for correcting them, and then also spending some time talking about some strategies for detecting them. More specifically, we're going to be talking about these categories. So mostly just like standard library types that you use day to day and how you are potentially creating extra objects when you write your code. So I've been saying extra objects, I've been saying unnecessary objects. What does that actually mean? We're going to kick off by looking at this sample code here. So we're initializing the string stir to be hello world. And then we're initializing stir2. We're creating it to just be a copy of stir. And then we go ahead and we print out stir2. So really it just seems like the purpose of this function is to print out hello world, right? And so it would be a lot simpler to just go ahead and directly print it out. And so we don't actually need stir. We don't actually need stir2. This second piece of code looks a lot nicer. And even with optimization flags, when you compile, the first and second don't become equivalent. The second is still generating much less code. And so stir and stir2 are unnecessary extra objects. Obviously, this is a very straightforward example, right? We're like literally initializing the extra objects. The ones that we talk about moving forward are going to be the ones that get created behind the scenes, but this is just the general idea that we're looking for. Why are these extra objects actually a problem? So C++ is a value semantic language as opposed to a reference semantic language. So on assignment, we're copying the value, not just the pointer. And so with something like this, where we have C and C1, C and C1 are actually going to be different objects. This second line here, when it calls the copy constructor, is actually creating a brand new object. Moving forward, we're going to replace that my class in that top example with actual classes like string vector. But before we get into that, I just want to highlight that we are overriding the operator new and operator delete. We're just printing out when they get called, so this way we know when we're allocating memory. So here's our first example. We're initializing this string s. This is a hello world string. And then we create s1 to just be a copy of s. And what we see when we look at the printed output is that operator new gets called 2 times, right? We're allocating memory when we create s. We're allocating memory again when we create s1 because that copy constructor is getting called. And allocating memory is a costly runtime operation. So if we can avoid that, that would be super beneficial. And so that brings us to using the move constructor. So instead, when we create S1, if we explicitly move, we see that there's only one operator new call. We're only allocating memory for the string one time when we create S. And that's because the move constructor of string is not allocating memory, it's swapping memory. And so it's still creating an extra object, but we are avoiding this memory allocation, so it's less costly at runtime. Of course, we are still creating an extra object, so that brings us to this third example here. We have this function getStir. We're returning our desired string, and then we set s to the output of that function. And we see again that operator new is only called once. We're only allocating memory one time for our string, which is good. And no extra objects are being created here. So this is in-place construction, specifically after C++ 17. This gives us in-place construction. In general, as we move through these slides, in-place is going to be preferable over moving, and moving is going to be preferable over copying. Next up, we've got vector. So similar example, but with vector instead of string. Here we have a vector v with 6 elements in it. We create v1 as a copy of v. When we look at the printed output, we see operator new getting called twice, right? We're doing this memory allocation when we call the copy constructor to create v1. If instead we use the move constructor, move construction results in operator new only being called one time. We're no longer allocating that memory when we create v1. Looking at stud list, here we have a list L with 3 elements in it, and then we create L1 to be a copy of L. Once again, looking at our output, operator new actually gets called 3 times when we create L, right? We're doing that memory allocation 3 times, and then it gets called 3 times again when the copy constructor is called to create L1. And so that's super expensive. If instead we use stud move, we see that operator new gets called 3 times to create it, and then not when we actually create L1. So it's not doing that extra memory allocation. So to summarize why extra objects are a problem, the object creation can cause these costly operations to be performed at runtime. So costly operations are things like memory allocation. They are things like making OS calls, running costly algorithms, etc. Extra objects can also cause more code to be executed at runtime, and they can need more memory. They can need more stack and heap space at runtime. So, of course, getting rid of them raises the question of what performance benefits will you get. To this, we say it's probably best to measure your own scenario. It depends kind of on what you're optimizing for. It depends on like your specific code and like your context, but it's super interesting to measure your own scenario. So I've been talking a lot about why extra objects are a problem when they're a problem. There are some cases where it's okay to create extra objects. That's typically for smaller data types. So plain old data types like int, float, etc. And then objects that we consider to be small in size and do non-costly operations in their construction are fine to create extra objects for. So things like string view, span, MD span, etc. To go a little bit deeper into what we mean by small, typically we mean that things that the standard library considers to be lightweight. So in general, things that are less than or equal to 24 bytes in a 64-bit system and don't do a lot of those costly operations in their construction, like don't have a costly copy operation, we can consider those to be small. So string view and span are 16 bytes in a 64-bit system, and dspan is 24 bytes. If you create your own user-defined type that meets those specifications, then we can consider it to be small. And then before I hand it over to Kathleen, I did mention that we want to give some strategies for detecting when this happens, in addition to just being able to detect the patterns that we highlight. And so these are some warnings and clang tidy checks that we'll be showing you throughout. I do want to highlight the 3 at the bottom there, W all, W extra, and W everything. Typically, we recommend using W all. W extra will catch a couple of extra things, and the W everything will probably catch too many. Throughout the slides, when we use a warning, we'll let you know in which of the 3 it's actually like automatically being used in. And with that, I'll hand it over to Kathleen.
Thank you. So now we'll look at basic strategies to avoid creating temporary objects. We'll start with a non-trivial type as a read-only argument to a function. So here we have a function foo that takes string s by value, and it's a read-only parameter. And this code calls foo. We're creating a string s that's large enough to defeat small string optimization and passing it into foo. We've also overridden operator new and delete again to see if a string is created when we call foo. Looking at the output, the call to foo prints operator new and delete, so it's allocating and freeing up memory when it's creating a string. In this case, it's better to use a const reference in the argument for foo. In the output, we can see no extra strings are getting created when we do this. As a rule of thumb, pass non-trivial read-only objects as a const reference and arguments to functions. Stud string is a special case, and we can use string view instead. String view also has some nuances we'll take a look at in some later slides. We'll look at the same example and see how we can use a clang tidy check, performance and necessary value param to detect this case. This catches the issue and suggests making it a const reference instead. If we use a string view instead, this doesn't get flagged, so this is fine to use. If we try making our own type, struct b, which is a simple type, and create a function foo that takes b by value, this also works fine with no warning. However, if we make a change to b and move the copy constructor out of line, this will get a warning. By moving the copy constructor out of line, b is no longer a trivially copy constructible type. The documentation for this check says it only applies to types that are not trivially copyable or have a non-trivial copy constructor or destructor. Now we'll look at returning a non-trivial member object of a class. We'll create our own type, struct A. This will be our placeholder type for non-trivial objects and examples throughout the presentation. It has print statements and all its special member functions to help us understand whether copies are being made. If the copy constructor is called, we'll see this printed. We'll try to improve on that by using move instead. And even better is emplace construction without any copies or moves. Now let's use struct A in our first example about returning a non-trivial member object. We'll define a new class called myClass, which has type A as a member variable and two functions, A which returns a const reference and A not great, which returns an object. This top code snippet uses A not great, and below is code that calls function A. And here's the output for both pieces of code. The copy constructor is getting called when we call A not great, but when we call A, which returns the const reference, no extra object is created. When returning a non-trivial member function or member variable from a member function, return it as a const reference to avoid an extra object. Now looking at the same example with the more optimal function A that returns a const reference, here we'll hold the return type as a const reference, and in the second piece of code, we'll make a small change to hold the return type as an object. When the return type isn't held by reference, the copy constructor is called to create an extra object. We'll now see if a clean tidy check can be used to flag this case. We still have the same example with some minor changes. So this highlighted code calls A without holding the return type by reference, and the second highlighted line creates a copy of object. When we use the clean tidy check, performance unnecessary copy initialization, this flags both the issues in the highlighted code, where we should use a const auto reference and a const myClass reference instead. Our next scenario we'll look at is using range-based for loops. We have this function getVec that returns a vector of n elements of our type A. This code calls getVec to create a vector of 2 elements, and then there are 3 range-based for loops, the first one using const auto, the second using const auto reference, and the third using a forwarding reference. And looking at the output, the const auto loop creates 2 extra objects, but the other 2 loops don't create any extra objects. It's better to use const auto reference or forwarding reference in range-based for loops for non-trivial objects. When we use the warning range loop construct with the same code, we get an error about using const auto in the loop, so it's a good warning to use. Let's look a bit more into the range loop construct warning and see if we can catch all issues. Here we have a struct A with one const member function foo and another non-const member function bar. In this code, we're creating a vector of strings and then using a range-based for loop using auto, and then we create another vector of type A and run 2 range-based for loops, the first using const auto and calling foo, the second using auto and calling bar. When the range loop construct warning is used, it just flags one of these cases, the const auto loop with a vector of A. When we use the clean tidy check, performance for range copy, it flags both the loop with the vector of strings, and again the loop using const auto for the vector of type A. It doesn't flag the third loop that calls bar, because bar is a non-const member function. Now I'll hand it off to Prithvi for the next section.
Thank you. Okay, so we're going to kick off by talking about structured bindings. Structured bindings essentially allow for the decomposition of composite objects, so things like tuples, structs, arrays. And so we're focusing on a struct. So this is struct B. It has this object of type A within it, and then our integer I. And this is 2 ways that you can use structured binding to get access to that object of type A within B. This first one uses const auto. The second one uses const auto ref. And when we compare the printed outputs, we see that the first one actually calls the copy constructor, whereas the second one doesn't call copy or move. So we're seeing an extra object being created in that first example, but not in the second one. So the recommendation here is to consider using const ref for read-only structured binding variables. Moving forward, we're going to talk about explicitly moving objects out of functions. So here we have 2 implementations of our function foo. They both create this object of type A, and then they return it. The first one returns it with this explicit move, and the second one just returns it directly. And when we take a look at the printed outputs, as expected, that first one calls the move constructor, right? We're explicitly calling move, so that's expected. But the second one doesn't call the copy constructor or the move constructor. Does anyone have any ideas about why that might be the case? Yes, exactly. So this is a case where named return value optimization or NERVO applies, right? In the second case, we have this named object that's being returned by value from our function, and so it can be constructed directly in the memory location of the caller's variable. In our first case, where we're calling that explicit std move, we're actually defeating this optimization. We're preventing it from happening. And so we want to avoid using std move in these cases. This optimization is not required by standard, but most compilers do implement it for such scenarios. So this advice holds for most of these scenarios. If instead we wanted to return our object of type A like so, this third implementation of foo, we see in this case, we also don't call the copy or move constructor, and this is because of guaranteed copy elision from C++17. It's also known as deferred temporary materialization and unmaterialized value passing. But all that to say, the compiler is essentially avoiding those unnecessary copies and moves. Um, of course, that kind of raises the question of like, how are we to remember, right? How do we know our compiler is doing this? How do we know that this explicit move here is causing a problem? And to that, we actually have a warning that can be used. So W pessimizing move, which is included in W all, will let you know like, hey, moving a local object in a return statement actually prevents that copy elision from taking place. There are some scenarios where Nervo is not going to apply. So here we have another scenario for explicitly moving on return. Our function foo here is creating this object of type B and then using structured binding to get access to that object of type A within it and then returning A. In the first one, we're returning it directly. In the second one, we're moving explicitly on that return. And when we take a look at the printed output, we see that the copy constructor gets called in the first case, but not in the second. And so this second version is a step up. This is not specific to structured binding. It applies in general to returning a member value from a local object in a function. So if we take a look at this example, where again, we're creating this object of type B and then returning the member variable A like so. The first one returns it directly. The second one uses that explicit move. We actually see the same result where the first one calls the copy constructor and the second one calls move. So the advice applies here as well. Okay, moving into the second part of this section, lambda captures. Here we have a function which creates this object of type A and then creates this lambda, which captures A by value, and then creates this second lambda, fn2, which is just a copy of that first one. We have a second function, very similar, right? Creates that object of type A, creates a lambda, creates a second lambda, but instead of capturing by value, this one captures by reference. And when we take a look at the printed output, we see that that first one calls that copy constructor when the first lambda is created, and then again when fn2 is created. And so in general, the advice here is when it's safe, capture by reference to avoid the copy. Diving a little deeper for lambda captures, we're going to modify our struct A that we've been using with these four member functions. They all capture to create and return a lambda. The first captures by star this, the second by this, the third captures by reference, and the fourth captures by equality. If we go ahead and call these get capture functions and then call the lambdas that are returned by them, we see this printed output. The main point here is that when you capture by star this, you do end up calling the copy constructor. So if you don't need to use star this, then try to avoid it because it will cause a copy of the object to be created. In this example, we are actually seeing that these lambdas are not actually using any of the captured member variables, right? It's just printing out this hard-coded string. So if we were to change that and instead make these get capture functions print out A, this actually results in a compilation error that we wanted to make note of. And the compilation error says implicit capture of this with a capture default of equals is deprecated. That's because if you're using C++20 or more, implicit capture by equality is deprecated. So avoid this fourth implementation of get capture. Okay, next up, we want to talk about what to do if you have a variable number of arguments. So here we have 5 functions that capture variadic arguments to create these lambdas and call them. The main thing here is that the bottom 2 capture these variadic arguments by reference. And when we call these functions, this is what we get in the output. We see that in the case where we capture the variable number of arguments by reference, we don't see the copy constructor call. So the advice here is to use reference capture with variadic arguments to avoid these extra copies. And with that, I'll hand it back to Kathleen.
Thank you. So we'll take a look at some strategies for reducing temporary objects when using string and vectors. We can use string view to stop creating strings at runtime. We have a function foo that takes a string by reference and another function foo better that takes a string view argument. In this code, we create a string stir, which is created at runtime. We pass the string hello to foo, and it creates a temporary string. Each time we call foo better, no temporary string is created. And here's the output of each function call. String view can handle string, const char star, and a const char star with length as arguments without needing to create different functions to handle each one. It also doesn't do any heap allocation. String view can also be used to create the string at compile time instead of runtime. However, in some cases, we can't use string view. If we have a function like foo platform here that expects a null terminated string, we can't pass the string as a string view because string view may not be null terminated. There's no C++ standard null terminated string view. Chromium has its own implementation of an alternative string view type, which could be used in this case. If you want to learn more about string view, you can check out this presentation by Jasmine and Prithvi from CPPCon last year. Let's look at an example where we have struct A, and it takes ownership of the string passed in its constructor or passed into the function setster. So these are sync scenarios. Instead of using string view here, we can follow the C++ core guideline for will move from parameters, pass by our value reference, and move the parameter. So we've updated the code here to follow this guideline. Looking again at the same code, we can use the clean tidy check, modernize pass by value to detect the same case and improve the code to pass by value and use move. Right now, this check only identifies this case in constructors. It's better to follow the C++ core guidelines from the previous slide, but the clean tidy check suggestion is still an improvement. Our next scenario we'll look at is using an alternative to string operator plus. We have 3 strings we're concatenating using the plus operator. You can see 2 temporary strings are getting created, and then a final third string is created. So in all, 3 strings are allocated memory. What if we have a function that concatenates strings more efficiently? So here we have the same 3 strings to concatenate, but instead of using plus, we're using a function called meistercat. You can see only 1 string is created instead of the 3 strings in the previous example. Does anyone have any guesses about how meistercat could be implemented? No? So here's, oh.
Sure.
Oh, okay. Were you going to say reserve?
No.
Okay, it's so here's our definition of meistercat. It uses reserve to ensure a single memory allocation for the concatenated string. Our definition of meistercat is inspired by the absol_cat implementation. If a string is small enough, no memory is allocated on the heap because string data can be contained by the string object itself. Temporary strings are still getting created though. In this code, there are 3 small strings being concatenated using the plus operator. No strings are allocated or deleted, but temporary strings are still created. If we use meistercat instead, no strings are allocated or deleted, and only 1 string is created. Meistercat is still optimal in this case because it only creates 1 string. Plus is only optimal in the case where there's a single concatenation and either one of the parameters is a string. Now we'll look at how to use string view subster to remove possible memory allocation. We have a function remove scheme, which takes a const string reference, and another function remove scheme better, which takes a string view. Both of these functions return a substring using s.subster. This code calls remove scheme and remove scheme better. So we can see when we call remove scheme with the const string reference, a string is allocated, but when calling remove scheme better with string view, no extra string is allocated. If we don't intend to modify the result of subster, we can use string view subster to avoid extra memory allocation. We just need to make sure when string view is used, the underlying string memory is valid. So we use reserve to prevent extra objects when concatenating strings, and now let's see how we can use reserve with vectors as well. In main, we're creating a vector of size 4. We use a for loop to emplace back 4 objects of type A. Operator new is called 3 times, first with size 4, then size 8, and then size 16 to resize the vector to hold the objects we're adding. The move constructor for each object is also called every time the vector is resized to move the objects into it. Let's compare it to an example where we reserve the size of vector before emplacing back objects. When we use reserve, operator new is only called once with the size of the vector needed, and the move constructor for A isn't called because no objects need to be moved. So reserve ensures there's a single allocation and no resizing needed. There's a clean tidy check you can use to catch this case in your code. So if you have emplace back in a loop, it will suggest you call reserve before the loop. We can also use span to prevent vector creation. So here we have two functions, foo and foo better. Foo takes a const vector reference, and foo better takes a span. In this code, we create a C-style array and pass it into foo and foo better. Passing the C-style array into foo forces us to create a vector. In the output, we can see calling foo created three temporary objects. Foo better created 0 temporary objects. Span allows functions to be used with C-style arrays without needing to create vectors. Using span also allows the function to work with other contiguous containers like vectors, arrays, and initializer lists. One thing to note is initializing the vector like this with an initializer list creates extra objects. We'll go over this case in some later slides. If we need a non-temporary object to be created, like in this case, we update A prior to calling pushback, it's better to use move. In the non-move example, the copy constructor is called, but when we use move, the move constructor is called. So it's better to use move to take ownership of the resources. And then I'll pass it back to Prithvi.
Thank you. Okay, we're going to chat temporary objects and common standard library types and containers now. So if we're kicking off with initializer list, which is what Kathleen just referred back to like 2 slides ago. So here we're creating this vector v using the initializer list constructor. And it's going to contain 3 elements of our type A. And what we see in the printed output is that 3 objects of type A get created, and then they get copied over to actually be in our vector. So we get these 3 copy calls. If instead we use reserve and then emplace back, we actually see that this removes the need for those temporary objects. The 3 copy calls no longer need to happen. We just see the 3 objects of type A get created. And so reserve and emplace back is actually giving us in-place construction. So this is our recommendation here. Moving forward into pair, here we have a pair with 2 elements of type A within it. And once again, when we look at the printed output, we see that those 2 objects of type A get created and then copied to actually be in our pair. If instead we use make pair, this gives us move construction. So we see in the printed output here, right, the 2 objects get created and then moved into the pair. If we use the CTAD version to create our pair, we get the same result. We also get move construction in this case. Of course, we're always aspiring to have in-place construction. And so to get that in-place construction, we need to use stewed piecewise construct. So it looks like this. It's a little bit more coding, a little more typing, but this does give us that in-place construction that we're looking for. We create the objects and then they're in place in the pair. Tuple is a pretty similar scenario. So here we have a tuple with 2 objects of type A within it. When we look at the printed output, we see them get created and then copied to be inside of our tuple. Make tuple, kind of like make pair, gives us that move construction. And then the CTAD version of tuple also gives us move construction. Of course, we want in-place construction. Does anyone have any ideas about how we could get that in-place construction? Yeah, that's a good guess. I think, yeah, piecewise construct is also a guess that I've gotten before. In-place T is also a good one. Actually, for whatever reason, tuple doesn't have in-place construction, so move instead of copy is the best that we can do. The omission is like kind of a hot topic, so we've linked the Stack Overflow post for why pair has piecewise construct, but tuple does not, in case you are interested. Next up, we're chatting optional. So here we are creating an optional of type A. We see that object of type A gets created and then moved into our optional. If instead we use make optional, this gives us in-place construction, and then that in-place T constructor, the in-place constructor of optional is also going to give us in-place construction. So the make optional is actually using the in-place constructor of optional behind the scenes. So in practice, both of these are doing similar things. So this is our recommendation for when you're handling optionals. In this case, we're setting the optional value directly when we initialize it. If instead we wanted to defer that creation, like an example like this, where we create that optional, and then somewhere down the line, we actually set that value, we actually see a similar result, right? We see that object of type A get created and then moved into our optional. If instead you use emplace, that gives you that in-place construction, so it's better for assignment. A quick note about emplace, it's actually going to destroy the current object before doing in-place construction if you do 2 creations for your optional. So here we have our optional, we set it to this object of type A 1, 1, and then we set it to 2, 2. And in the printed output, you see that that deletion of that first object happens before the in-place construction for the second. Okay, next we're talking about expected. So here we have a function foo that's returning a student expected with the success type of A. And we see, similar to optional, right, that object gets created, it gets moved into our expected. If instead we use the in-place constructor of expected, we get in-place construction. It removes that need for that temporary object. So our recommendation is for non-trivial success types of student expected, use the in-place constructor. Unexpected, which is the error type of student expected, actually requires us to create a second struct here. It's very similar to A, it's our error struct, but it's also printing out in all of these special member functions. There are a couple ways that we can go about creating this unexpected. The first is this one here, where we create the unexpect like so. We return it from our function. Our return type here is an expected, and this actually results in us getting two moves. Once when we create that expected, once when we create that unexpected, and then once because of that return type. If instead we use the in-place constructor of unexpected, this gets us down to one move, right? We get in-place construction when we create that unexpected, but our return type is still an expected. And so finally, the best way to go about this is to use the unexpect constructor of expected. And so the unexpected constructor of expected is going to give us that in-place construction that we were looking for. So for non-trivial types being used in the error type of student expected, our recommendation is to use that. Okay, next up, we are talking variants. So here we have a variant of type A. You see that object of type A get created. It's the same pattern, it then gets moved into the variant. If instead we use the in-place type or in-place index constructors, that gives us that in-place construction. It removes the need for temporary objects. So for non-trivial types being used in variant, that's the better way to go. In this case, again, we're creating that variant and then initializing it as we create it. And so if instead we wanted to change the value type, so do something like this, where we have our variant v, it's actually going to get initialized to an integer with the value 0. And then we want to change it to instead be a variant of our type A. We see this result. So the object gets created and then moved into our variant. If instead we use emplace, that gives us that in-place construction, so it's better for changing types for variant. So using emplace when you do want to do this this sort of behavior is our recommendation. If instead you wanted to change the value but not the type, then you could have a scenario here like this, where we create that object of type A, we set it to be this object 0, 0, and then we want to change it to be another object of type A, which is 10, 10. And we see here that we have this extra operation happening. So emplace actually works better here too. It gets rid of the need for that extra operation. Of course, we're still creating two objects of type A. That's expected since we're dealing with two. But we get rid of that extra operation happening. Similar to what we talked about with optional, we just want to make the same note about emplace. It's going to cause the destructor of the current object inside a variant before doing the construction for the second. So emplace is better for both the non-changing type scenario and then also that changing type scenario that we just looked at. Okay, next up we're talking about toArray. So here we're using toArray to create this array with two elements of type A in it. This looks pretty nice, right? You don't have to specify the number of elements. You also have to write A one time. However, this does give us a two move constructor call, so one for each of the elements that we're adding. If instead we create it directly like so, not as nice, you have to specify the length, you have to write A before each of the elements that you add. But it does give us that in-place construction. So this is a better direction to go in. You can use the deduction guide, and that gets rid of that need to specify the length, which gives us some of that niceties that we look for with toArray. But in general, to create a student array of non-trivial objects, consider using the array constructor rather than using toArray. And then finally, the last thing we want to talk about is adding elements to vectors. We're going to make one quick modification to the struct A that we've been looking at. We're just adding this member variable at the bottom here. And what we're doing is we're printing it out when our special member functions get called. So the big change here is that you see A of 10, and then you see the copy constructor call with 10 and the move constructor call with 10 being printed out. In our actual code example here, we are creating this vector, and then we want to add two elements to it, 0 and then 1, and we're using pushback to do it. And we see here that there's two move constructor calls, right? One for that 0 and then one for that 1. If instead we use emplace back, we no longer have those move constructor calls. And so emplace back is allowing for this in place construction to happen. So using emplace back instead of pushback is the recommendation. For this, we also have a clientele check that you can use that just lets you know, hey, as a warning, use emplace back instead of pushback. This clientele check also works for other iterative containers, so stack, queue, forward list, etc. And then finally, this emplace replacement for some sort of push insert function is a pretty common pattern. So here we've just summarized some of them for other iterative containers. So these are the emplace back, emplace front, emplace after, etc. alternatives for pushback, insert after, things like that. For deck, forward list, list, stack, queue, and set. And with that, I'll hand it back to Kathleen.
So we've looked at many types of sequence containers, and now we'll take a look at more examples with associative containers. First, we'll look at using emplace with maps. Here we have a map M with key type string and value type int, and we're creating a key of string hello and setting the value to 10. So this creates the string and moves it into place. Now we'll look at maps with non-trivial types. In this example, we'll use our user-defined struct A as the key type and int as the value type. We create a map and assign key A10 to the value 10. A temporary object is created and then moved into the map. If we instead use emplace, we get in-place construction. In this case, the key is a non-trivial object. Let's look at the case where the value is a non-trivial object. Here we have a map with key type int and value type A, and use a subscript operator to assign a key of int 10 to an instance of A initialized with a value of 10. And this code actually does not compile. Struct A actually needs a default constructor for it to compile in this case. Once we've added that, we can see why, as it creates an object using the constructor that takes an int and another with the default constructor, and then uses the move assignment operator, and two objects are destroyed. If instead we use emplace or try emplace, the constructor is only called once and no temporary objects are created. So we can see emplace and try emplace do in-place construction even if the value is a non-trivial object. Let's take another look at when the non-trivial type is the key in a map and see if emplace and try emplace behave differently. We'll look at the basic case, not using emplace first, where the key A10 is assigned to the value of int10. This creates A and moves an object. If we use emplace instead, only one instance of A is created and destroyed, so no temporary objects are created. Let's look at try emplace. Does anyone have a guess of what the output will be? As emplace? It's a trick question. So it's actually the same as the first example using the subscript operator, where the constructor and move constructor are called, and two objects are destroyed. If the key type is a non-trivial object, then only emplace allows for in-place construction. There was a paper accepted for C++26 that added support for try emplace and the subscript operator to allow them to behave the same as emplace in this scenario and do in-place construction. Now let's look at how emplace works for constructors with multiple arguments. We have a struct B that accepts two ints in its constructor. We'll use this in a map with key type B and value type B. We get a compilation error if we try to pass 4 ints in to try to create 2 instances of B, so we can't do that. Instead, we have to create 2 instances of B. So this calls the constructor and move constructor for both instances of B. Let's see if we can improve. Here we'll use piecewise construct with forward as tuple. This only creates 2 instances of B. This approach, using the piecewise constructor of pair, does in-place construction. If we use try emplace, the key object gets created and moved, but the value object gets created in place. Therefore, it's better to use piecewise construct. Now let's look at when the key already exists in the map. Here we have a map where the key is an int and the value is of type A. We emplace the key 10 with a value of A initialized with 20, and then emplace another value A30 to the same key. There's also an example for try emplace here to compare to emplace. No extra objects are created, even after emplacing and try emplacing different values. For an existing key, the value type object was not created. However, this is not guaranteed by the emplace specification, but is guaranteed by try emplace. Next, to take a look at insert or assign, we'll use the struct to see when objects are created. This is similar to what we used in the previous slides, but this time it takes two ints in its constructor, and it's a template, so we can name two identical types, key and value, as defined at the bottom of the slide, so we can see when the key and value objects in our maps are created and destroyed. With this code, we can see how types are used and when the constructors are called for each key or value object in the output. So using these structs, we'll create a map with types key and value. Here we're seeing what happens if we try to insert and assign objects to the same key. First, the key object k is created, then the value 2020 object gets created, then the key value pair gets created, which calls the copy constructor for key and the default constructor for value. Value 2020 is moved into the value of the pair, which was inserted into the map. And then lastly, we assign value 3030 to value associated with key 1010 in the map. Let's compare to what happens when we use insert or assign. This is doing the same thing and assigning a different value to the same key. And the difference is highlighted here. Insert or assign moves the inserted value object instead of using assignment. If you have a function that does both insertion and assignment, use insert or assign instead of the subscript operator. And then back to Prithvi.
All right, thanks, Kathleen. Okay, so we're chatting transparent comparators to avoid extra objects. So this section is going to apply to 4 associative containers. We're going to be focusing on set, map, unordered set, and unordered map. The first thing that we're looking at here is this set of stewed strings. Once again, we're overriding operator new and operator delete, just like we were all the way at the beginning, just so we can see when we're doing memory allocations for the strings. And so the 3 methods that we want to focus on here for our associative containers are going to be count, contains, and bind. So in our function, we're going to initialize this set S. It's going to have key types, element types of stewed string. And then we're going to initialize our test string as a C-style chart array. And we're going to try to check the count, the containment, and if we can find that test string. Of course, our set is empty. We're not going to be able to find it. But the other kind of surprising thing is that we're creating these extra objects, right? We're allocating extra memory to create these strings on every call to count, contains, and find. And so what appears to be happening here is because our test string is this C-style chart array, it's going to try to convert that to a stewed string and then check containment in our set for it. So to do a little sanity check, if we change our test string to instead be a stewed string instead of the C-style chart array, we actually see that when we call count, contains, and find, we don't have any operator new calls because we're not allocating any additional memory for a string, right? We only see operator new calls when we actually initialize that string. And so ideally, we get this behavior for things that are not just stewed strings, right? We get it for our C-style char arrays. We get it for our char stars, our const char stars. And so going back to our broken example here, right? This is our C-style chart array. It's causing these extra memory allocations, these operator new calls. If we go ahead and we throw in this stewed less, this transparent comparator, we actually see in the printed output that we no longer have those operator new calls. We no longer have that extra memory allocation happening. Then just to do another sanity check, make sure that we're not regressing any behavior. We can go back to our previous example where we were checking this stewed string as our test string. And that stewed string was matching the actual element types in our set. And we now have that transparent comparator when we initialize the set S, and we don't see a regression or anything like that in our printed output, right? No new operator, new calls as expected. So our guidance here is when you're initializing a set of strings to use the transparent comparator stewed less to avoid these extra memory allocations. And so temporary comparators allow comparison to happen without the need to create these extra temporary objects. They're identified by this is transparent type def, which you see at the bottom of the libc++ implementation of studless, which we've copied over here. If we take a look at map is similar. Here we have a map where our key type is the stud string. If we call the three methods that we've been looking at, count, contains, and find, when we see the printed output, we also see these operator new calls. We see this extra memory allocation happening because that C-style char array is getting converted over to our key type. Instead, if we use our transparent comparator studless, we no longer have those operator new calls. And so the same strategy applies for map. If you throw in that transparent comparator when you initialize your map, that's going to prevent the need for these temporary objects. Okay, next up, we're chatting unordered sets. So here, unordered sets have the element type of stud string. When we call the same methods, we see the same result, right? We have these operator new calls, same pattern. And so we want to add a transparent comparator. The transparent comparator for unordered sets is a bit different. It looks like this. It's myString hash and equal to. So myString hash is implemented like so. It has this is transparent type def, so it can be used as a transparent comparator. It meets that requirement that we were talking about earlier. And it also adds a function calls to allow hashing from const char star, string view, and stud string, which would have worked anyway. And so our recommendation for unordered sets is to use myString hash and equal to get transparent comparison. And then finally, unordered map, very similar to unordered set, right? We see the same problem as before. We have these extra string allocations happening. If we put that myString hash and equals to in there, we no longer have those extra allocations. So it's better to use that when you initialize your unordered map. So we have a slide that just kind of summarizes this advice. So studless for set and map, and myString hash and equal to for unordered sets and map. All right, I'll hand it back to Kathleen.
Oh, thank you. So our last topic, moving data to compile time. In our previous examples, we were talking about how to create objects in place to prevent temporary objects from being created at runtime. Instead of creating them at runtime, we can create them at compile time. Memory for compile time objects is constructed at compile time, which improves runtime performance. If we have local objects like this, where we have a const string or vector, the const means we can't modify them. We can move them to compile time by making them static const expr string view or arrays instead. Let's look at global strings and vectors. If we build using flags global constructors and exit time destructors, we get these errors. This helps identify opportunities for moving global objects to compile time. So we can make them const expr string view and array instead, and move them to compile time. Here are the global string and vector again. These global objects are created before main starts. One way we've seen people on our team try to defer global object creation in our codebase is to make them magic statics. Here we have a static const object being returned by reference in getStir and getVec. The claim flag exit time destructors will also point out magic statics. Magic statics fixes the global constructor issue from the previous slide, but not the exit time destructor error. Sometimes if we move const data structures to compile time, we'll need to make some changes to the usage. For example, here we have a function getVec that returns a const vector reference to global array. Instead, if we convert global array to a const expr array, karray, getVec will need to return a span instead. The calling code may also have to change. We just looked at moving string and vector objects to compile time, but what if we have a user-defined data structure? So here we define a struct sum class that contains two strings and an int. We have a const global vector containing objects of this struct, and a function that searches for a string in any of the objects in the vector. And this code gets the compiler warning that the declaration requires an exit time destructor and a global destructor. Instead, if we make a new vector in getArray and return a reference to it, we don't get a warning. Now the function containStir calls getArray. Absol no destructor can also be used here to annotate the scenario. We can also change our struct to use string view instead of string and array instead of vector, so we can move our user-defined data to compile time using const expr. In our codebase at work, we've seen quite a few instances where we could convert user-defined data structures to compile time. Another scenario we can improve is concatenating strings. In this example, we have two context for string views, and then when we concatenate them at runtime, the result will always be the same. In this case, we can use a custom class, myCompileTimeStringJoiner, which we'll look at on the next slide, to do compile time concatenation. When we use this, we have a compile time concatenated string. And this is the implementation of myCompileTimeStringJoiner. It was copied from this Stack Overflow post, so you can create your own class like this for your own codebase. You can also check out Jason Turner's video from C++ on C last year for more info about creating compile time strings. So can we move set and map to compile time? There's no standard compliant way to do this. Chromium has defined fixed flat map and fixed flat set that can be used to create compile time set and map. Stewed flat map and flat set were added to C++ 23, and they will be made const expr in C++ 26. Once they are const expr, then some additional code can be written to create their instances at compile time. Until then, you can consider writing your own symbol wrappers. And so that's all the topics we're covering today. So to recap the key points, we want to have in-place construction without copies or moves. To do this, we can pass non-trivial objects by reference, use view types like string view and span, use in-place constructors for STL types, use emplace and containers, use transparent comparators, and move data to compile time if possible. You can use claimed tidy checks and warnings to identify potential improvements. And a special thanks to our colleague Chandra, who helped with this presentation and encouraged us to be here. Also, thanks to the C++ community for all the great articles and videos that made this talk possible. Does anyone have questions?